So there are two different strategies we're going to use to compare the empirical and simulated or posterior predictive test statistic values in this case. The first strategy is to use what's called a posterior predictive p-value. And in many ways, this is similar to the more sort of standard frequentist p-values that we're familiar with. So if we think about our distribution of posterior predictive values represented by this solid curve in figure 6 here. And we think about the empirical value, which is represented by the vertical dashed line on the right-hand side. In this case, we're going to calculate what's called an upper one-tailed p-value. And so this tells us what fraction of our posterior predictive test statistics are larger than the empirical test statistic. So if our empirical value falls right in the middle of our simulated posterior predictive distribution, then the posterior predictive p-value is going to be very close to 0.5. If the empirical value is in the right-hand tail, so if it's rather large compared to the simulated values, then we're going to get a fairly small p-value. And if it's in the left-hand tail, then we're going to get a fairly large value. So because we're using this one-tailed approach, p-values near either 0 or 1 indicate relatively poor model fit, and p-values somewhere in the middle of the distribution, so closer to 0.5, indicate good fit. So they indicate that the empirical value is a reasonable draw from the posterior predictive distribution. It's expected given the assumptions of the model. The other kind of value we're going to use to compare the empirical and posterior predictive test statistics is called the effect size. And the effect size in this case measures how far away from the median of the posterior predictive distribution the empirical value is. But it's measured in units of standard deviation. So how many standard deviations away from the median is the empirical value? So if the empirical value, again, is entirely reasonable given the simulated values, if it falls right in the middle of the simulated distribution, the effect size is going to be very close to 0. And as it is farther and farther away, the effect size is going to go up. Now, one advantage of using effect sizes compared to p-values is that they can distinguish between cases where our empirical value falls just outside our simulated distribution from cases where our empirical value is very, very far away from the values that we've simulated. In the case of a p-value, it's going to be close to 0 or close to 1 in both of those cases, no matter how far away the empirical value actually is from the simulated distribution. So in some ways, the effect size gives us a more sort of continuous sense for how different the empirical value is. So to calculate our p-values and our effect sizes in this case, in our Rev code, there's no built-in function to calculate a p-value given a vector of simulated values and an empirical value, so we're going to go ahead and create one. So here we've created another custom function just called p-value, and it takes 2 arguments. The first argument is a single value, e, for empirical value. And the second argument is actually a vector, s, and this is the vector of the simulated test statistic values. And so all this function does is it goes through each of the simulated values and it asks, is it greater than the empirical value? And if so, we're going to tally all of those cases, and then we're going to calculate the fraction of simulated values that are bigger than the empirical and return that value. So again, this custom function here, this custom p-value function, is just telling us how big this gray shaded area is in figure 6. So if we go ahead and calculate those p-values, so we define that p-value function, and then here we just calculate what those p-values are for each of our 4 test statistics, and then we can report them. And then we're going to go ahead and calculate the effect sizes here. So we do this by taking the difference between the empirical value and the median of the simulated values. And then we take the absolute value of that because we want to keep track of cases both where the empirical value is far to the left and far to the right of the median. And then we're going to normalize by the standard deviation. And then again, we're going to do this for each of our 4 test statistics. So for the mean test statistic, the median, the first percentile, and the 90th percentile. And then we're just going to print those values out just like we did the p-values. And so if we do that for our test case of this single normal distribution, we should get a result that looks something like this. Your results should be a little bit different. The values shouldn't be exactly the same, and that's just because the simulations are stochastic, and so they're going to vary from run to run. So you'll see we do get different p-values and different effect sizes depending on which test statistic we look at. So for the mean, we get a p-value that's very close to 0.5, so it's very close to the middle of the distribution. For the median, we get a p-value that's very large. And so what that means is the empirical value is in the left-hand tail of our distribution. So most of the simulated values are larger than the empirical value. For the first percentile, we get a value that's very small. So the empirical value is actually in the right-hand tail of the distribution. And for the 90th percentile, we get a p-value that's sort of intermediate. It's not quite exactly 0.5, but it's not so far away from 0.5. So it's in the right-hand side of the distribution, but it's not all the way out in the tails. And the effect sizes correspond roughly to the p-values. So again, for the p-value near 0.5, we get an effect size that's very close to 0. For the relatively large p-value associated with the median, we get an effect size approaching 2. For the first percentile with the p-value near 0, we also get an effect size near 2. And then for the p-value of 0.3, we get an effect size somewhere in the middle, effect size of about 1/2 of a standard deviation. So well within the bounds of our simulated distribution. So that's really the end of the code that we're going to use to perform posterior predictive model checking. And we've walked through the code bit by bit, but if you wanted to run this analysis all at once, you could also just use the source command in RevBayes to run all the code in that rev file at the same time. Now for posterior predictive model checking, it's also nice to graphically compare your empirical and simulated values. Unfortunately, there's no built-in way to do this in RevBayes, but it's fairly straightforward. If you take the values you've generated in RevBayes, you can plot them fairly easily in something like R or Python. And so that's what we've done here. So just to reinforce the results we saw earlier, actually starting at the bottom, we have the mean test statistic, and you can see that the empirical value represented by the arrow falls right in the middle of our simulated distribution. For the 90th percentile in green, the next one up, the empirical value is slightly to the right, but still well within the simulated distribution. For the median in red, the empirical value is fairly far out in the left-hand tail. So this is the case where we saw a very large p-value. So most of our simulated values are larger than the empirical value. And for the first percentile test statistic, it had a very small p-value and relatively large effect size because it's out here in the right-hand tail of our distribution. So these 4 test statistics are actually behaving quite differently and telling us different things about our model. They're assessing different aspects of model fit.